basically looking at the development of the electron quantum mechanical model today. But before we can do that, we have to go back over light and waves, because that's where the initial development came into the dual nature of being particle properties, wave-like particles together as electrons do have. Okay, and the first picture, of course, fireworks. That goes along with, we were talking about stuff we did last year. A lot of it you'll hear about and remember from last year, because we did the flame test lab, which is why the fireworks have their pretty colors, is because the electrons jump, they fall back, they give off the energy and so forth, and we'll be going back over those concepts as to why we did that lab last year, okay? And everybody, I'm pretty sure, did that lab last year, okay? So, skipping that because we pretty much just answered those questions, but electromagnetic radiation. So this is your first thing. What are the three characteristics here? They're going to have a wavelength, they are going to have a frequency, and they're going to have a speed. Wavelength, frequency, and speed. So that's 1, 2, and 3. Okay? Now, the symbol for wavelength that we use is a Greek symbol. So it's lambda. Right here, it looks like this. It is a lowercase lambda. Okay? And that's always going to be the symbol for wavelength. Wavelength is the distance between two peaks or troughs. Peaks also are known as crests in the wave. Okay, and you see the wavelengths on your diagram on your paper, which we'll show that slide in just a minute. But as you see the different of those three, the wavelengths get shorter as you go down. Frequency, which is kind of this italicized V here, the number of waves or cycles per second, also known as hertz. So 1/second is the same thing as hertz. And it passes a given point in space. So it's really the oscillations of the waves. Oscillations, okay? And then the speed is always the speed of light. All electromagnetic radiation is going to be measured at the 3.00 times 10 to the 8th alpha. However, it is on your formula sheet, okay, just so you know, and it's actually more precise than that measurement that most people use. The one on your formula sheet says 2.998 times 10 to the 8th, meters per second. So most people just round it to 3, but this one is on your formula sheet, okay? Along with our lovely formula here. Speed of light equals wavelength times frequency. This is on the formula sheet. So you will have it provided to you on the test, okay? So it's right here under atomic structure. Make sure that, and we'll do some practice with our formula sheets to make sure we know where to find stuff quickly, okay, for our AP exam. Okay? So far, so good here. Now, based off of this equation, speed of light equals the wavelength times the frequency, you should be able to do exercise 1. Okay? There is one little glitch that you have to pay attention to when you're doing these. Oh, before we get to that, let's look at our frequencies here, and we'll need to discuss some relationships here. So the first wavelength from here to here, it's longer. Then on the second wave here, the wavelength gets shorter. And then it's even super short here. But as you see, the frequency is also, wavelength's getting shorter, but the frequency is increasing. Okay? So if lambda is going down and getting shorter, V is increasing. It is an indirect or inverse relationship. And later on, we'll be attaching energy into this as well. And things that have higher frequency, guess what? They have higher energy and are more penetrating, like gamma rays and X-rays on the spectrum. Much higher energy because their frequencies are much higher. Okay? So frequency and energy have a direct relationship, whereas wavelength and frequency have an indirect, and therefore wavelength and energy are going to be indirect as well. Longer the wavelength, the lower the energy. The higher, or the shorter the wavelength, the higher the energy and frequency. Okay? So keep that in mind that you see these relationships between these three variables: wavelength, frequency, and energy. But you'll see the energy equation coming up in just a few slides. So that also brings us to, knowledge of our spectrum here. Okay? Gamma rays, like I said over here, this is going to have the highest frequency and also the highest energy. Down here, this guy is going to be the lower frequency and have lower energy, but the wavelengths are pretty big. Okay, and your wavelengths over here are going to be very short. My little lambda symbol doesn't look so good over there. Let's fix that. Okay, so wavelength short, frequency and energy are high. Wavelength is long, frequency and energy are low. Okay, but as you can see, this is all we get to see because this is the visible spectrum. We don't get to see a whole lot. So blue is down here at like 400 nanometers to red, which is about 700 nanometers. That's all we get to see. Ultraviolet, just above violet, X-rays and gamma rays, they're all cancer-causing, because they have the high penetrating energy and so forth. Okay? So just a few little tidbits there before we go to exercise 1. Now looking at exercise 1. The only problem with this is that they give us the wavelength in what? Nanometers. And what is the speed of light in?
Meters per second.
In meters per second. So we have to do a quick conversion before we're allowed to use it in our equation. Does anybody remember the conversion factor for nano? That would be micro, -6. -9. They jump in threes at that point. Pico is going to be -12. Nano is -9. Micro is -6, and so forth. So you can do it one of two ways. This is how I convert it. I do 10 to the 9th nanometers equals 1 meter. However, you can flip them and do 1 nanometer equals 10 to the -9 meters. Either or should do the trick. And you still end up with 6.5 times 10 to the -7 meters, right? And now we can easily use RC equals lambda V, because now we have our wavelength in meters, and we can use the speed of light to determine the frequency. I believe that's what we want here, is frequency. We want the frequency of red light, so then you would just plug in your 3 times 10 to the 8th meters per second, and your wavelength, 6.5 times 10 to the -7, times your frequency, and divide, and you quickly get your frequency. This equation, like I said, is on the formula sheet. You aren't expected to memorize it. You just need to be able to work the problem. And in your problem set, you'll have some of these in the beginning as well. Okay? So if we plug in chug, what do we end up getting here? Yes, we're going to end up getting 4.6 times 10 to the 4th. 10 to the 4th or 14th? 14th hertz, or you could write it as 1 over seconds, depending on how you want to write your unit. 1 over seconds is the same thing as hertz, so that equals your frequency. Now going back to the idea of quanta. Quantized energy, quanta, mechanical model, quanta, you see that a lot in this whole area when we start discussing things. Max Planck explained it by assuming that energy comes in packets called quanta, which is a fixed amount, so it's more of the staircase analogy, okay? Is it possible to go halfway up a stair? No, it's not, right? You either have to go entirely up the stair or you stay at the stair you're on, right? It's an all or nothing deal. Same idea there. And that's how these photons and electron particles and other things work. It's in packets. So it's like a stair. You have to meet the entire get to the entire height before you can move on, or you stay at the level that you're at, okay? And we're going to be talking about electrons absorbing and releasing energy, but they release it in amounts that are fixed, and we call them quanta amounts, okay? So keep that in mind when we're talking about quanta. We mean fixed amounts. It comes in packets, okay? So before we continue on, we're going to talk about the photoelectric effect. And we're going to get into the energy equation in a little bit, but you don't have to write it down just yet, okay? So I'm going to switch over here and show you this quick little video. Oh, that's not what I wanted. Nope, back. Sorry. Yes, it is. Well, we'll get right to the right video. Hold on, there it is. Okay. And I will turn on the sound, and then you can hear. All right. So pay attention. Hold on, it's not loud enough. We'll make it a little bit louder.
Electric effect is the ejection of electrons from a surface when light of sufficient frequency shines on it. For example, when red light is directed at a metal surface, no electrons are ejected. However, when blue light, which has a higher frequency, is directed at the metal surface, electrons are ejected and a current flows through the wire as measured by the ammeter.
Okay, so as you see there, the red hitting the metal, no electrons got ejected. Didn't have a full packet of energy, a quanta. It wasn't able to make it move. The blue, though, we know has a shorter wavelength, has a higher energy, was able to eject those electrons off the metal. Okay, so as that one went over the amount, the quanta amount allowed it to eject the electrons, and they got some voltage through. So that's where Einstein was able to use this idea, this quantized idea, in order to explain how electrons work on the metal surface like that. Okay, and they apply, this application was being applied to light energy, electromagnetic radiation, photons, but later on we're going to apply it to the electrons, and that's how it developed into the current model for the electrons. Okay. So back to our other one. So don't worry just yet about writing this down. We'll get to Planck's constant too, which is also on your formula sheet in just a minute. So energy is quantized. That means that it's gained or lost in whole number multiples. That is like the fixed amount we were talking about before. Okay? Energy is gained and absorbed in fixed amounts. Okay? And we'll get to it later, but it does seem to have particulate properties too, meaning the behavior of particles. Okay? So that's what we're talking about when we're talking about saying something's quantized. It has this fixed amount. It evolves in a whole number of multiples. It's like the staircase. Okay? Energy is absorbed in like the idea of stairs. Okay? So what is a photon? It's some kind of stream of the electromagnetic radiation. Stream of those particles are called photons. So X-rays, gamma rays, radio waves, infrared, all of them come in streams of photons. Visible light, photons. Okay, now the equation we were talking about on the previous slide is this one. Energy equals Planck's constant times the frequency. Don't worry about the one on the right just yet. That's how we would derive it if we wanted to put the two together. Okay? So, Planck's constant, 6.62 times 10 to the minus 34. It's joules times seconds. This one is on your formula sheet. So you do not have to memorize it if you don't want to. So Planck's constant's on your formula sheet. Now, and talk about deriving here. If E equals hv and C equals lambda v, both of them have frequency in them, right? So can't you put them together? Right? Right, so if I made V equal E divided by H and V equal C divided by lambda, couldn't I say then that E over H equals C over lambda? And then I could eventually get to that point, right? So you can put the two together to calculate them faster if you'd like, or you can plug and chug and then plug it into the next one. Some people like to do it in steps. That's okay. Okay? But you can set them equal to each other and plug for the missing variable. If you have all of those to look at, I believe like in exercise 2, you have to do that as well. Okay, so exercise 2. Blue color in fireworks is often achieved by heating copper 1 chloride. This compound emits blue light having a wavelength of 450 nanometers. What increment of energy is emitted? So if you have the wavelength, what else do we automatically know? We know the wavelength because it gave us to it, just change it to meters first, right? What else do we automatically know? Speed of light and Planck's constant. So you can solve for energy pretty easily, right? So go ahead, let's go ahead and solve that one. I'm just doing the quick conversion from nano to meters here, okay? And we end up getting what? .4 times 10 to the minus 19 joules. Yes, joules, because remember this is joules times seconds here. Seconds will cancel, the meters will cancel. You could, do all of the unit canceling here. Okay? And we end up getting 4.4 times 10 to the minus 19 joules. Actually, just need one more sig fig because I see it here now. It has 3, so we would add on the 2, make it a 2 there. Mm-hmm. Well, here they wrote it with the 1 0 on the end, so I'm assuming this is what they meant to base off your sig figs. Yes. Well, we'll come back to it at the end if you need to. Okay. All right. Moving on to energy having mass and the dual nature of light. So we're talking about having wave-like particles, or wave-like properties, which we just talked about, or like electromagnetic spectrum properties. Now we're talking about being able to have the properties of having mass and being a particle rather than just energy waves. Okay? So electromagnetic radiation in all matter exhibits wave-like properties and particulate properties, which means like particles. Okay? So that's where we get the dual nature of light. And it eventually evolves into the dual nature for the electron as well. So So really all you need to write down here if you're writing is the fact that it has wave-like and particulate properties. This we're going to use to derive being able to incorporate mass into the equations. And yes, you're going to see kind of a little bit of physics here evolving. Okay, so on exercise 3, after we look at the de Broglie equation, you'll be able to see that. Okay, you're like, oh yeah, this is physics class all over again. So here, the only problem is, just like we said before, like you have equilibrium K, we have K constant for kinetics K. Well, they do the same thing here sometimes between physics and chemistry, where some variables look very similar. In this case, we're talking velocity is now V, not frequency. Okay? H is still Planck's constant, and M is going to be mass in kilograms. Mass in kilograms. But you can figure out the wavelength. You know the mass, the velocity. So technically, if you're walking or running or moving at any time, you're giving off a wavelength. Anything that has mass, if it's moving, is going to be giving off a wavelength. So that's what you're going to do now in exercise 3, is determine the wavelength and compare them from the electron, comparing it to throwing like a baseball and seeing how the wavelengths might be. So I'll give you a couple of minutes to go ahead and do that. Not that you really know this, but you might, I don't know. A joule is actually equal to a kilogram times meter squared divided by second squared. So yes, that is how the units nicely cancel out, but if you didn't know, that's what a joule equals, which is, a joule is a derived unit, by the way, based off of the Newton somehow, and all this comes together. But more physics stuff for you, just to mind you. Just so you know, yes, there you have it. Okay, did everybody get these answers? Yes? Good. Comparison, who has the longer wavelength? The electron does. As you see, more massive you get, the smaller your wavelength and all that good stuff. So let's get on from hopefully the physics stuff and get on to more of the electron stuff, but a lot of it does involve physics. Now, some development of our current model came from Bohr, so we're going to talk a little bit about Bohr for a moment. Another mystery in early 20th century involved the emission spectra, observed from energy emitted from atoms and molecules. Okay, so the line emission spectrum versus the continuous spectrum here. The continuous spectrum, when you refract it through a prism, you get the beautiful rainbow, as you see over here. Okay, white light gets refracted, you see beautiful rainbow. On the Lyot spectrum, though, if you put like a gaseous component inside the tube and you have the light go through it, through the slits and so forth, you end up with only distinct lines up here. So this kind of ends up being like the atom's footprint, fingerprint. Okay. So as you can see, hydrogen produces 4 distinct lines of color. Now this is going to go with its one electron, and what its one electron's doing, you're going to see in a little bit. Although neon down here, neon has 10 electrons, we call it a polyelectronic atom because it has more than one, which is everything but hydrogen. As you can see, it forms a whole lot more lines and has a lot more energy change possibilities than hydrogen does. Okay? So the line has discrete wavelengths observed. It's not continuous, but it applies to each element only, as you'll see. Okay? And you end up with your distinct bands in there. Okay?
White light that is passed through a prism separates into a rainbow or continuous spectrum consisting of colors from violet to red.
Okay, so that's the white light. Now we're going to take a look at emission spectrum. It will let me move. No, it's not letting me move, so we'll just do it that way. Okay.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
Okay, so we're going to learn as to why that is. Just a moment, back to the presentation here. All right, so the significance. Why is it important? Significant. Only certain energies are allowed for the electron in hydrogen. Those certain energies, are those packets or quantized energy that we've been talking about. So they only allow certain ones, okay? Those quantized amount of energy, and it only allows it absorbs a certain amount so it can jump to an outer energy level. You remember this from the flame test lab, and then when it falls back, after it's absorbed the energy, it falls back, it gives off the energy in the form of photons. That's why we see pretty colors. Those are photons coming off, and we get our nice flame tests that we've done before. Okay? So that would be our significance when it comes to the line emission spectrum of hydrogen. Okay? So we're going to be able to calculate using the equation that was developed and derived below, and you see a nice big constant there. Okay? All right. You don't really need to write all this down, but I just want to show you as remembering flame test. It absorbs energy, it jumps out. And then when it releases energy, it falls back to the principal energy level, n equals 1. That would be energy level 1 versus energy level 2, 3, 4, and so forth, going up. Okay? In his model, of course, he had circular orbits, so you could see it represented in this graph. Or you could see it represented, well, there's another one where it shows the jumping and it shows you the 4 distinct lines that you saw in the video there. Okay, but you could also see it in the round circular ones. Going out further, if you go out just, one ring, it's not as far of a distance, so you don't have to absorb as much energy, therefore your wavelength's going to be longer. That's why you're seeing red there. Longer wavelength, lower energy, because the distance to jump isn't as far. Jumping out further, you're going to have shorter wavelengths because you're going to need more energy, and therefore you're going to be giving off one of the shorter wavelength colors. And of course, the further you go out, you get more into the purples because those are the higher energy ones and so forth. And that's what you were seeing last year when you were burning all those metals and doing the flame test lab. All right, so back here to our equation, which is already on your paper. You can actually calculate the energy transition. And from the energy, when you get energy, you can also go back and use the energy equals Planck's constant times frequency to figure out the frequency, and then you could figure out the wavelength by going over to the speed of light equation. So you can be told the transition for hydrogen and be able to figure out which color it's dealing with. Okay? So the first thing to do, though, is realize that your final, is the last destination where the electron is. Your initial is where it started. Okay? So if we're looking at some examples here, We know Bohr's model was incorrect. It's not circular orbits. His model only worked for hydrogen. Not a big deal, but we did get our principal energy levels out of it. That idea and concept came from there. So if we're starting here at principal energy level 5, this would be like the initial. And we're falling back to 2, this would be like the final. Okay? Now you need to do a series of calculations here because you're going to find the E. And then remember, once you find the E, you can do the E over H, what equals C over lambda, and then you can switch spots and do lambda equals what, HC over E. So we're going to be looking for the wavelength, okay? So do a calculation, try to find the wavelength at the end from it. Okay, so first use your delta E equals a negative 2.18, whatever it is, constant there, times 10 to the negative 18 joules, that equation. Okay, figure out your energy, and then you can plug it in here. Now, one also thing to note, if your delta E comes out negative, what does that mean? It means energy is released. Just like in endo and exothermic. If your delta E comes out to be positive, it means it's being absorbed. Okay, just like in endo and exo, just so you know. And when you're falling back, you're usually releasing, so your number is going to come out negative. That doesn't matter. That's just the amount. You can plug it in this equation and still discover your wavelength. Just realize that only the negative positive is there to denote which way the energy is going. Is it releasing or absorbing? Yes. You'll figure out the wavelength and then you look it up on the spectrum. Like 400 is going to be in your purples, 700 is up to your reds. Now, of course, you can't see it very well on your black and white paper, but if you grab one of those chemistry textbooks on your desk, you can open it up and find it there as well. So calculate a few of those real quick. So if you've done one, you've done them all. Check out, see if you get the one that's going to have the longest wavelength is going to be red, orange, which happens to be the shortest jump. But think about it. Use intellectual capability of conceptual knowledge here. Distance to jump, less energy, longer wavelength. Okay, so keep those like direct and indirect relationships in mind about energy, frequency, and wavelength as you're working these. Okay, so you don't have to work out every single one. If you can do one, you pretty much can do them all. And yeah, I believe in your problem set there's a couple of these, but you do have the electromagnetic spectrum in chapter 6, so you can see like which color is which wavelength. So be able to look that up there. Okay? So just so you know, you can write, you can jot down the answers or you can revisit the PowerPoint on Blackboard if you'd like. All right, Heisenberg's uncertainty principle. You do not need to write all of this down. Please do not. All you really need to know about this is that there is a fundamental limitation about knowing the position and the momentum simultaneously. We cannot know both at the same time. If you know the momentum, then the position is uncertain. If you know the position, then the momentum is uncertain, and so forth. This is the actual equation if you were to calculate it, but you don't really need to know that for our purposes. Okay, you can calculate it. And like there's a calculation example in the textbook where it talks about the momentum of the electron, and it gives you an uncertainty of like 1 times 10 to the minus 9 angstroms or whatever it was. But for hydrogen, and if hydrogen's only like 1 times 10 to the minus 10 in size, you basically don't know the position of the electron at all, because that's almost the same distance as the radius of the hydrogen atom. So we don't really need to write it all down. You just need to know that from this idea, Heisenberg's uncertainty principle, we can know the position and the momentum at the same time. And this led to Schrodinger being able to figure out the wave equations, and where we got the current quantum mechanical model of the probability of where the electrons are going to be. So all you really need to know and write down is that it's not possible to know the momentum and the position at any given time for an electron. Okay? So keep that in mind. So he developed a mathematical, you don't have to write really anything down from here either, mathematical way of determining the wave and particle nature of the electron. And it ended up falling under the umbrella of quantum mechanics. We're going to talk about that electron density graph in just a minute. But this is what you need to write down about Schrodinger and what we use it for. Square of the wave equation. This is psi, Greek symbol psi, gives a probability density map of where an electron has a certain statistical likelihood. Well, basically 90% likelihood, okay? 90% likelihood of where it's going to be. Now, if you're looking here at this graph over to the right, okay, that is like an elapsed time graph of where the electrons have moved and been mapped at, okay? If you look here, okay, low dot density value probability of finding the electron there is pretty low. And the high dot area, so this is the high dot area, okay, that's the likelihood of where you're going to find the electron, okay? And if you look here, it's kind of forming a nice little spherical shape there, and this particular graph is going to be denoting which orbital, which type of orbital. An s orbital. Remember s orbitals? Okay, s orbitals are spherical. So they look like round, spheres around the nucleus, which the nucleus would obviously be, dead center on the map there, okay? So his wave function's a very high level bit of physics here that we're not going to get into, way beyond the scope of this course. Allows us to be able to see these densities and be able to predict where the electrons are going to be 90% of the time. So when you write out an electron configuration and you're putting electrons, when you're putting electrons in, say, like the 2s or the 3p or the 4d or whatever, you're really saying this is where we believe it's going to be 90% of the time. Okay? So that's the purpose here of Schrodinger's equations and wave functions. Okay? No, you don't need to write every little bit down, I promise. Now, we need to talk about orbitals, because this is where the important application level and where your problems are going to be coming from. Okay? The wave equation gives us a set of wave functions or orbitals and their corresponding energies. Orbitals and their energies. Each orbital describes a spatial distribution. So it's like a 3D space. 3D space where that electron's going to be. Okay? The orbital is described by 3 sets of quantum numbers. And yes, we have to go back over quantum numbers, and I know we didn't spend a lot of time on it last year. I know my group got about a day and a half of quantum numbers. So you might recall some of it, you might not. It might be like, oh yeah, I remember what n is, but I don't remember what L is, or m sub L, or m sub s. We're going to go through the quantum numbers again. Okay? But once again, you're not writing everything down. You need to realize what we're doing is the orbital. It's a 3D spatial arrangement of where the electrons are going to be. Okay? And we describe where they are using quantum numbers. Okay? Principle of quantum number n. Everybody knows quantum number n? When we say principal energy level, this we're talking about where the orbital resides. Okay? Principal energy levels, we use what to figure them out? What do you use to figure out the principal energy levels? The what? What? The row, yes, on the periodic table. That's what I was hoping to hear, is periodic table. We use the periodic table, yes. The row you're in on the periodic table, yes, row. Slash period. How many rows or slash periods do we have? 7. So there's 7 principal energy levels. Now remember our periodic table method, the S and P's are equal with their principal energy level rows. The D's and the F's are off a little bit, but we'll talk about that in a minute. So we use our periodic table to denote, so periodic table. This is how we figure out our principal energy levels. Okay? Okay? Yes, that's what we were going for. Thank you. Okay? Now, principal energy level N, you just go with the row that you're in to figure out its particular quantum number. Okay? The angular momentum number, known as L. Okay, this is the L number. The quantum number defines the shape. That's all you need here, is the shape of the orbital. That's all you need to know about L. On the next slide, I want you to write down what's on the next slide. You don't need to write all the rest of this down here. We use the letter designations S, P, D, and F, but their L numbers never change. They're always the same L numbers. You can just memorize it off of that. Okay? So, you wrote down shape of orbital. Let's go over which orbitals go with which number. S-shaped are always going to be zeros. P shapes are always going to be 1 for their L, D shapes are always going to be 2, and F shapes are always going to be 3s for their L's. Okay? So, if I said my electron is located in 4D, my electron's located in 4D, my first 2 quantum numbers, the first one would be a 4, because that's my N number. My second number would be a 2, because my L is a D, right? So N is 4, because that's the principal energy level. L is going to be a 2, because we're in a D shape. Okay? So far, so good. Following the quantum numbers again. Because now we're going to get to the tricky one, M sub L. That one's the hardest one, I think. The magnetic quantum number describes the orientation of the orbital. Orientation of the orbital. Now, what do we mean by orientation of the orbital? Remember, if we had a P, right? A P sublevel, right? Remember those were 3s? D's had how many of them in there? D's had 5, right? Okay. So, the D's are a little bit harder to visualize because their shapes are really funky. But the P's are pretty easy because the first one is the P on the X plane, the second one is the P on the Y plane, and the third one is the P on the Z plane. They have one on each plane at the coordinates there. So, which one are you in? Are you in the X one, the Y one, or the Z one? And this is how you label them when it says like negative L to L. So this would be -1, 0 to 1. So if my electron was in this one, my M sub L number is going to equal 0. If my electron was over here in the PZ and it was pointing down, okay, so this one would be, my M sub L would be 1. I know, it's going to come together all at once in a minute, but anyhow. Okay, we'll get to the spin one, the plus half, minus half in just a minute. I know you're already thinking about that, the plus half, minus half ones. Okay. So it gives you a nice graph of, if you'd like to look them up in your book, but like I said, We'll come to some examples here in a minute. Let's talk about the shapes, though, before we try to put all the quantum numbers together. S's are always spherical. This is all you really have to write. They're spherical in shape. They just get bigger. As you get further out from the nucleus, they get wider. They get bigger spheres. That's all the difference there. Spherical shaped ones. Okay? Now, that's all you have to write there. Looks like a sphere. Okay? The P's, though, we call them. Before we get to the P's, let's talk about these graphs real quick. They show you these graphs where here is the distance from the nucleus and the probability of finding the electron. Okay, so of course we know that they fill the lowest energy level possible. We'll go back over Aufbau principle later on, but likelihood the 4s is going to be the closest to the nucleus because it has the lowest energy. Yes, an electron would fill there first. Then here in this graph, this is showing the 2s, this is showing the 1s, this one's showing the 3s. Now, most of the time, the likelihood of where you're going to find the 2s electrons are further out, a little bit further away from the nucleus. Occasionally, they squeeze in from time to time and get closer and move back out. Once again, this is 90% of the time, though, so it's not perfect. It's not like everybody's in their fit little box all the time. Okay? As you can see on the 3s one, the majority is even further out from the center of the nucleus. It's getting that wider sphere and so forth. Okay? Looking at the P's. This is what the density graphs look like. They have them up and down. But as you can see, the P's look like dumbbell shaped. Okay, or that's what they're called. You have one on the z-plane. Here's one on the z-plane. Here's one on the x-plane. And then you have one on the y-plane. Okay, so you have one on each plane. That's why there's 3 in the sublevel. Okay, 3 different p orbitals, all shaped like dumbbells. Okay, they have the 2 lobes and the node in the middle. Okay. Now, I'm going to skip the videos. If you want to watch them spin, you can look up the PowerPoint. The D's. You don't have to know a shape for the D's because guess what? The D's are starting to look a little funky. They look like 4-leaf clovers, but this one right here is like a donut shaped. Okay? And realizing that these are the 3-dimensional shapes as to where the electrons are going to be. So envision me here, with my 5 lines, right? The 5 lines of the D sublevel, right? When I'm putting something in this box right here, or this line, it's going in that shaped orbital. If I'm putting something in this one, it's going in that shaped orbital. So the third one, of course, that one, the fourth one is that shape, and then the last one is the funny donut shape looking one. Okay, so when you're placing the electrons into their orbitals, that's what you're doing, is you're actually placing them into those 3-dimensional weird looking spaces. Okay? And the D's look kind of funny, so I'm sure you can imagine the F's are even more intricate and have a lot more shape to them. But before we get to them, as you can see, these are the density graphs again. You can see the density graphs and how they kind of make those 4-leaf clover shapes there. Okay? Just another reference to the data showing that, where they are 90% of the time. Now for the F's. As you can see, the F's have 7 orbitals in the sublevel. They are even more intricate in their shapes. These are where the electrons are. They travel around in these little areas, okay? I know, quite a lot of intricate math involved in all of that, like I said, way beyond our scope. So when I'm placing something in like the first orbital of the F, we're placing it in the first orbital right here, this funny donut-shaped looking one, okay? Exercise 5. For principal quantum number n equals 3, determine the number of allowed subshells or sub levels and the different values of L for each. Okay? So that's a lot of information. In principal energy level 3, what can I have? What are my possible ones I can put things in? I can put it in an S, true. For principal energy level, n equals 3, we have a 3s. What else do we have? A 3p, good. We do have a 3d, very good. Do we have a 3f? No, when did the f start? Principal energy level 4 is where the f starts. So in this particular case, we would only have an S, a P, and a D possible. Okay? Different values of L here. So what would the value of L be for this guy? This is 3 for its N number. What would its L number be? 0, right? This one would be 3, and then it would be a 1. And this one would be a 3, and it would be a 2. Now, if we wanted to denote the particular orbital it was in, we would have another number there, and then if we wanted to determine the spin, we'll have the 4th number there. We'll get to the spin in just a minute. Okay? So L equals 0, 1, and 2 for the S, P, and the D. Subshells are the same thing as sublevels, by the way. If you hear that, sublevel, subshell means the same thing. Okay? Let's look at the next one. Exercise 6. Is it exercise 6? For L equals 2, determine the magnetic quantum numbers, M sub L, and the number of orbitals. What could that be? First of all, if L equals 2, what kind of level are we in? We're in a D. Good. So if L equals 2, we're in a D. So, number of orbitals. What's the possible number of orbitals in a D? How many orbitals does a D have? 5. 5 blanks. 5 boxes, right? So that could be like 3D or 5 lines. Some people draw them with the lines like that. So if you're in L equals 2, you're in a D. A D has 5 boxes or 5 lines, so you're going to have 5 orbitals. Like remember, 4 of them were like those clover leaf shapes, and one had the weird donut-looking thing. Okay? So that would be what you would put there for a question like that. Okay? Your magnetic quantum numbers will range from -2 to 2, so I guess I could have drawn that out there. So if this is my D, -2 starts here, and it goes to 0, and then it goes the opposite direction. So if you put an electron right here, 1 arrow up, this one, say it was a 3D, we would be 3 for our energy level. We would be a 2 for the sublevel D, and then our third one would be a 1 because that's the particular orbital that it's in. So this orbital would denote there. And if I wanted to, I could tack on, because it's spinning in the up direction, it would be +1/2. So if you remembered your spins, it's +1/2 -1/2. If you're spinning downward, so if we were doing an electron from here, say I was doing this one, the one that's pointing down in the first one, my 4 quantum numbers would end up being 3 because of the 3, 2 because of the D, and then -2 because that's the orbital it's in, and then -1/2 because it's spinning downward. So quantum numbers, we'll go over a few more examples with that. We're going to look at the magnetic spin here, the 4th quantum number, in just a moment. Okay? So the electron spin number, M sub S, can be +1/2 or -1/2. Those are your only 2 choices. And this is where Pauli exclusion principle came into play. Pauli exclusion, okay, in a given atom, no 2 electrons can have the same set of 4 quantum numbers. So that really tells us that each orbital can only hold 2. So that's really what we're going for, is that they can only hold 2 electrons. because that last quantum number, if it's plus a half, minus a half, nobody's going to have exactly the same address. Okay, and plus a half, minus a half, it looks like it's spinning upward and downward. It's really spinning like a top, and it's spinning clockwise and counterclockwise. Okay, so for instance, say we're in a p sublevel, we'll say we're in the 2p. Okay, 2p. I have electrons. Okay, let's say I'm 2p5, right? Everybody remember 2p5? I have 5 electrons in my 2p. That makes me 1, 2, 3, 4, 5. That makes me fluorine. I'm fluorine. Okay? If I filled up through 2p5, I'm fluorine. Okay? So, but if I wanted to address the quantum numbers, say on this guy right here, what are the 4 quantum numbers for that particular electron? 2 is my N number, right? Because I'm in energy level 2. P is my sublevel. So what number do I assign my L number to be? 1. Okay? Now, this is -1, 0, 1. So my M sub L number is going to be a 0 because I'm in the middle one, right? And last but not least, which direction am I going? M sub S, I'm going downward, so I'm -1/2. So that would be my list of quantum numbers for that particular electron.
Oh my gosh.
Does it make sense now? Coming to you? Coming back? Okay, hopefully coming back to you, yes.
More time. There is a point where
okay. So that's just denoting the 4 different numbers. You have N, then L, then M sub L, then M sub S. They're written in that order, and they do have commas between them, yes. And you'll see them in problems denoted exactly like that. Okay, just so you know. Does everybody see that? Just making sure we're all on the same page. Okay, and once again, you don't really have to write anything down about this real quick. But knowing that the quantum number was, detected by a magnetic field, because spinning in different directions, you're negative, you create a magnetic field. Okay, but I do want you to get this visual aid here, because we see the arrows, we put them up and we put them down in the boxes, so we think spin up, spin down. They're actually spinning clockwise and counterclockwise. Okay, clockwise and counterclockwise. So I wanted you to get that visual representation as to, which direction they're going. Okay, so the spin up is really clockwise, the spin down would be counterclockwise. Okay, and going back to that whole idea that we're only going to be able to have 2 electrons in an orbital. Okay, that's Pauli exclusion principle, and you have to have them having 4 different quantum numbers. That last quantum number is going to allow us to have the difference. Okay, and now going on to some of the stuff from last year that's a little probably more. Oh, no, we're going to go into the penetration effect first. Which way do they prefer to fill? They prefer to fill the lower energy, right? Lowest energy to highest energy. So that's kind of following off-bow principle, starting at the bottom and working your way up. But we know this is the case. S's will fill before P's, before D's, and before F's. So that is the particular order that they're going to follow when they're filling in their possible energy levels, sublevels, and orbitals. Okay? They can't be calculated exactly. We know this because of uncertainty and all of that good stuff. Okay? They prefer the lowest energy level. That's why they're going to fill S first, because S is going to be closer to the nucleus and have lower energy than the P. That's what we're talking about there, the Y, okay? Orbital energies. Oh, yes, I do want to show you this one. Hang on a second. All right, pay attention, please.
In a hydrogen atom, all subshells for each end are at the same energy. For multi-electron atoms, the subshells are spread apart due to interactions between electrons.
Okay, so if you watched it, you would have seen that hydrogen only has one electron. So I'll replay it real quick. If hydrogen only has one electron.
In a hydrogen atom, all subshells for each end are at the same energy. For multi-electron atoms, the subshells are spread apart due to interactions between electrons.
Okay, so that one looks more like the off-bow diagram that you've seen, where it kind of looks more like a staircase, or like our mountainside party house that everybody did, the house party. Okay, yes, you remember that? Yes. That is because in hydrogen, there's only one electron. You don't have interactions of the electrons. We know electrons are negative, so they repel other electrons. So keep that in mind, that the energies are equal in hydrogen, but everybody else has more than one electron, so they actually end up varying a little bit in their energies. So generally, the 1s is lower than the 2s than the 2p, but the 2s, say in nitrogen, isn't the same energy as the 2s in titanium. Relatively, yes, the 2s is going to be lower than the 2p, but they're not exactly the same calculated energy for each individual atom. Okay? So keep that in mind. One last little note before we leave today. The penetration effect. Penetration effect. The 2s electron penetrates to the nucleus more than in a 2p orbital. This causes the electron in the 2s to be attracted to the nucleus more strongly. Okay, and that makes it have lower energy if it's closer to the nucleus. So the 2s orbital is lower in energy than the 2p because it's simply attracted more to the nucleus, that positively charged nucleus. Okay, and that's what creates this stair-step case in the off-bow diagram. Okay, in those polyelectronic atoms, because there's more than one electron. Okay, some electrons get pulled closer, and that particular orbital is lower in energy. Okay, and then we get our different stairs in our off-bow diagram, allowing for different, like the 1s being lower than the 2s is lower than the 2p, the 2p is lower than the 3s, and so forth as we travel up. Okay? So what you can do, because your problem set is due on Friday, you can start working on all of the wave calculation problems, because there's like, I think like 6 or 7 or 8 wave calculation problems, so that you don't leave it all for one night. So you can start that tonight. Wednesday we'll finish the notes, and you'll be able to do the rest of the problem set. Some of the problem set goes over your periodic trends. You're welcome to read the textbook if you want to get a little ahead, but there are a few little exceptions to the periodic trends. They are noted in the textbook if you'd like to read ahead, but that might give you a little bit more jump on your problem set due Friday. Okay?